Now that we have a bit of an understanding of how CodePeer works behind the scenes, let's take a look at a demo for CodePeer. This demo is based on the Simple Desk Calculator tutorial that comes with both GPS and CodePeer. And at this stage, I've opened the project, but I haven't really done anything else. One of the early things you'll want to check is that there is a CodePeer menu that is going to be there so long as GPS finds the executable for CodePeer in the search path, the normal executable search path on Unix or on Windows. So you have to be sure that your executable search path is set up to include the uh, directory in which the binaries of CodePeer are stored. And in this case, in this installation, it's in user local GPS bin, but yours may be elsewhere. Anyway, so if we have a CodePeer menu, that's a good sign. And at this stage, all we need to do is analyze all. That's one of the great things about the integration between CodePeer and GNAT front end is that it's essentially a one-button integration. And as you can see, there's a progress bar showing us what's going on. And once the analysis is complete, it will put up this top-level CodePeer report, which gives us a summary of the various kinds of messages that CodePeer has produced as a side effect of analyzing the various pieces of our source code. If you remember correctly, the first step was for it to generate skill files, that's statically checkable IL files for each of the source files. And then the CodePeer tool proper, or engine, if you will, starts up and then analyzes all of those skill files, identifies places where it thinks there might be a problem or a suspicious code, and then produces this report plus messages for individual issues. So here we have SDC, which is our simple desk calculator, and then we have a subsidiary project, which is the runtime library, but we're not going to be worrying about that in this demo. Okay, so by opening up this small desk calculator project, we see the set of source files that have some number of messages. Notice we have a color coding here. There's high ranking messages, medium, and low. This ranking is done using a tailorable pattern file called the message patterns file. And you won't want to fiddle with it right away, but over time you may have project specific rankings that you'd like to introduce, and there's a way for you to do that. Okay, so in this particular demo, I'm going to drill down into the file stack because I think it has an interesting first issue to deal with. So if I click on stack, I'll see that down here in the locations window, we have a messages window which has the where we see the actual output of the tools as they're running, and then locations window has the individual messages on each line. And this is the one I want to start with, medium warning, suspicious precondition for last, not a contiguous range of values. And I'll explain what that means. So I click on that, and it brings up the source code for the file in which this message occurs. And here we see that it's showing up in orange. It's medium. Yes, that's orange, not red. Red would be a little darker. It shows up on orange, and in this case, it shows up right on the header of the procedure. And now we make sense out of what this message says. It says there's a suspicious precondition. Okay, well, I think I mentioned that CodePeer generates as-built documentation, and what that means is a set of comments that describe the properties of this particular subprogram, stack.push. Some of those properties have to do with preconditions, that is, what are the restrictions on the inputs to this subprogram that must be satisfied to avoid various kinds of runtime failures while in this procedure. So it's saying that the input last, which is a global variable in this case, notice that v is the parameter input, but last is a global variable. And we could look up, well, I guess I'll scroll up here if we can find it. There it is, last. It's just a natural. And it's initialized to an index into this array here. This is actually our stack represented as an array of values going from 1 to size. Last tells us essentially how many elements there are in the stack. If last were 0, that would mean there was nothing in the stack. And last would be going up as you put things on the stack and going back down as you go down the stack. So tab is our stack. So here we are, and it's saying that as a precondition to push, last must be in the range 2 to 199 or 201. Well, that looks like a fairly suspicious precondition. It's not uncommon to have some kind of a range, but to have a discontiguous range like this one where there's a gap. What happened to 200? Why is 200 not allowed, but 201 is okay? And what about 1 and 0 and so on? We're a little suspicious about what's going on here. So the way CodePeer works is it analyzes each subprogram and infers from that subprogram the preconditions by looking at what values of inputs will cause it to fail. And for example, tab tick last is 200. We could make certain of that, but tab goes from 1 to size, and size is 200. So 200 is the maximum value of an index that can be used with tab. And so when we enter stack.push, the first thing we check to see if is last equal to 200. If it is, then we immediately raise an exception. So from CodePeer's point of view, you don't want to pass in 200. That's why it's not mentioned here, because if you pass it in, it would cause trouble. So there's a precondition that you not pass in 200. But it's a little odd that it's okay to pass in a number larger than 200. Let's look what happens. If we pass in 201, last is not equal to 200, so that's okay. So we make it past here. Then we print some message or other. We subtract 1 from last. Now it's 200. We use it as an index into tab. Well, that's okay. On the other hand, if we had passed in 202, subtracting 1 would give us 201, and then that would overflow. So we can see why numbers that are larger than 201 would cause an index out of bounds here. The thing that is a little odd here is that this is a push routine, but we're subtracting 1. Let's look at what pop does. Well, pop pulls the value out at location last, and then it also subtracts 1. One of these must be wrong. And if we look back at the representation of this stack and the notion that an empty stack is 0, clearly as you push, you should be increasing the number of elements in the stack. So the fact that this precondition is suspicious is often an indication of some kind of off by 1 error. If you have a gap in the range of values for an input, CodePeer in its experience, or the developers of CodePeer, have recognized that these kinds of discontiguous ranges on preconditions tend to indicate there's some flaw in the logic. And in this case, there is a flaw. Instead of being a minus here, this should have been a plus. Some sort of a cut and paste error must have occurred. Or somebody's finger slipped, or who knows. Or we put the bug there just so we could see it. So having made that fix, now all we need to do is reanalyze. So boom, analyze all. And we can see the progress bar there going, and blom, 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 working, working, working. Now you might not necessarily always do it this way, make one fix, try it all over again. But we have the luxury of doing that because this is a relatively small file. And so now let's see what happened. So going back to our stack, boom. Well, there's nothing there. There's no suspicious precondition there anymore. If we click on this one, we'll see that this complaint is occurring on a different line down here in the view procedure. We look back up at our push procedure over here. No more message, no more complaint here, no more red bar. Furthermore, the preconditions now look a little different. If you remember correctly before, last had a rather strange looking thing. It had to be in the range 2 to 199 or 201. Now it has a much more reasonable looking restriction. That is, it must be less than or equal to 199. So any value, 0, last is a natural, so it couldn't be negative, but 0 is allowed, 1 is allowed, all the way up to 199. Those are all fine. And that makes pretty good sense. We come in here with 200, it will still raise an overflow. Anything larger than 200 we will add 1 to it, and then we'll try to use it as an index, and that would overflow. So CodePeer has recognized that 200 and above are trouble. 199, okay here, add 1 to it, that's 200, that's fine, because tab does have a 200th element. So 199 works fine, as does everything down to 0. 0, add 1, that's gives you 1, use it as an index here, and that's fine. So this all looks much better now. We have successfully fixed one bug, and now we'll move on to the next case. So let's go back to our CodePeer report. And this time I'm going to look in the tokens file, and it says medium array index check might fail. Okay, well, let's click on that and see what the source code is associated with that. So here we have our bright red bar, and at line 26, yeah, sure enough, line 26, column 18, well, I'll take your word for that on. And it's worried about the possibility that this index might be out of bounds. We're using word tick first index into word. And it requires that that index is less than or equal to the low bound of word, and I'm sorry, that it's greater than or equal to the low bound, and that it's less than or equal to the high bound being word tick last. And the issue here is that suppose word, which is the result of calling the next word function, is the empty string. Well, tick first for an empty string is generally 1, and tick last is generally 0 for an empty string. Or anything where the last is less than the first is considered an empty string. So we are, at this stage, just blithely assuming there's at least one character in word, and there's no guarantee of that. In fact, we can double check that there's no such guarantee by clicking on next word. We can click twice to get to the body. There we have the body of next word. And one of the nice features of this as-built documentation is we can look at this to conclude what did CodePeer decide were the possible results of calling this function. And here we have it's saying the input.nextWord inputs the file we're in. NextWord is the function. Tick result, that means the result of a call on this function, is a string, return string, and its low bound is going to be less than or equal to 1024. Okay, well, we'd have to look through to believe that, but I can believe that. And its high bound, tick last, is in the range 0 to 1023. So right there in black and white, we see that there is the possibility this could return the empty string. So this little bit of as-built documentation informs us why CodePeer is a little bit nervous that here we are making our use of word, which was returned from nextWord, without worrying about the fact that it's might be empty. So how do we solve this problem? Well, this one, there might be better ways to do it, but in this particular case, I'm simply going to put in a little defensive coding here. So let's check to see if word equals the empty string. So then what do we do? Well, if we look down here, we see that for other kinds of syntax errors, this remember is a desk calculator. The user is supposed to be typing in something that might be understandable by a little desk calculator. And if they type in some random mysterious character, they're going to get a user error, which will be propagated and hopefully handled, and with giving the user appropriate error message. So we'll treat this like a syntax error. That is, if they just give us the empty string, then we will raise except. Oops, I can't spell. Except, maybe I can a little help here. Except dot user error. Okay, semicolon. And so now we'll put in the end if, semicolon. And now we've done a little defensive coding, if you will. We've turned this into something other than a constraint error. That's what would have happened if we had actually got an empty string here. We would get the runtime check failure. But here we're doing our own explicit check, and CodePeer will now notice that we have ruled out or eliminated the possibility of reaching this code in the case of an empty string. And if I'm lucky here, I will analyze all, rerun this, and CodePeer should be happier. So our little progress bar there has indicated that it's finished resolving. Now we'll drill our way back down into the input routine. And here we are with our new version of next. And we can now see there are no red bars. There are some or orange bars. There are some yellow bars, but those are a little less scary, I suppose. And two of them relate to the conditional check. It might raise an exception. And this one corresponds to this new piece of code we added. So CodePeer is generally designed to inform you of all places where an exception might occur, both from built-in checks, where generally the exception is constraint error, or one of those, that kind of thing, or user-defined exceptions. Well, presumably user-defined exceptions are somewhat lower concern. We put them in explicitly, so we sort of know they can happen. But CodePeer still tries to identify ones that could occur, and but we can make a choice that don't want to see those anymore, at least not today. So what we're going to do is we're going to go back to this CodePeer report, and over here on the right we have all kinds of capabilities of filtering out certain kinds of messages. And the one that we're not particularly interested in today is conditional check. So let's uncheck that. And now, boop, disappeared. So if we go back to tokens, and we look at our this routine, those errors are no longer being shown to us. And we don't see any yellow here. There is still a concern at this line where it's worried that the first character might be uninitialized. And we'll, at the moment we're not going to deal with that. But it's still worrying a little bit about that next word routine. Apparently it can return, at least in some cases, uninitialized data. So it'd be interesting to investigate that, but we're not going to go into that right now. Let's go back and turn the filter back on so we don't forget about it, just so and sure enough, these things reappear, and there's our little yellow line again. Okay. Another thing that would be worth noticing here is that over here we have a message history. I think I mentioned in the while I was giving the PowerPoint presentation that there is a historical database, and every message that is produced by CodePeer on any execution is recorded in the historical database. So suppose we wanted to focus only on messages that are removed. So what messages went away? Well, that's interesting here. We had this message, tokens, and it's saying that on line 26, there used to be a message about an array index might fail. Well, this was line 26, but there's no such error now, but this is telling us that it, in fact, did exist before. And we could look at, in general, all of the removed messages, and there was one in tokens, there was one in stack. That was our suspicious precondition has gone away, and so on. So we can look back in time if we want to see what messages have been removed. Similarly, we can see, well, what messages have been added. And there was one new message here in tokens, and it's a conditional check might raise an exception. So sure enough, this is a new message that didn't exist before. Well, this is also new code that didn't exist before. So it's not surprising that there might be a new message there. And as we saw before, we could simply filter that message out or filter it back in. Okay, so so that's over here. I'm going to bring back the unchanged messages. We normally leave it in this state. We want to see all the new messages. We also want to see all the messages that haven't been removed. And we don't want to normally see the removed messages because that's just going to confuse us because we'll think we fixed the bug and we didn't. But the removed can be useful when you're trying to see, well, what went away. Of course, the line numbers may not match anymore, as we saw it didn't in this case, but still we can identify what messages did we in fact fix, which might have been our ultimate goal. Okay, so let's just look at one more warning here. This is in the values procedure. Medium warning, unused out parameter. This is sort of interesting in that it identifies whenever we call a procedure that has an out parameter. If we simply ignore that out parameter, that might be a little suspicious. Now, not always. There are cases when there are out parameters that are of no interest. But in this one, this routine read number, if we go over and look at it, we'll see it has an in parameter, the first one, and then the rest are all out parameters, an integer, a float, and a number kind. This is a little bit of an unusual procedure. I'm not certain I would recommend this, but you call it without knowing whether it's going to be an integer or real, and it tells you in the number kind what sort of thing it is, either no number, int number, real number. And if it's an int, it fills in I. If it's a real, it fills in R, which isn't totally unreasonable, but a little unusual, I would say. In any case, depending on the number kind we're informed of, that will probably imply we'll only look at one or the other of these two out parameters, I and R. So if we go back to the place where this call was, if the kind is not an int, we only accept int. So it's a funny thing to use this routine that takes either, but this is a simple desk calculator, not a complex desk calculator. We raise an exception syntax error. So we're not prepared to handle that. Perhaps we should have said not yet implemented, but in any case, we're throwing this back on the user. And then we create a little object here called a value info object, and we use the value that was returned by read number. We never do anything with real val, so it's completely ignored. And that's a little unusual, and we highlight it here. Now, we don't really want to see this message every time we analyze this procedure, so let's put a little comment into this historical database. It serves two purposes. One, the historical database keeps track of what the messages were before and what they are now and so on, so you can do comparisons that way. But it also allows us to annotate and say that the automatic ranking mechanism said it was medium. But let's change it to intentional. We intentionally are ignoring real value. We are intentionally, always bad to type in front of other people. I think there are too many I's there. Ignoring real val for this simple desk calculator. Well, I got a couple of typos. But anyway, I think that gets the idea across. And let's now record that in our database. Ba-ching! And now notice that message has now been suppressed. So we have the ability to suppress messages, or let's say hide them, in two ways. In the CodePeer report, we could simply uncheck something, and then those wouldn't show up. And the other is we have the ability to explicitly suppress one particular message that we think is not of interest. Now, that information is retained in the database, and there are modes on the tools that will show you all such individual message suppressions, so that if you want to go back and double check that the person who suppressed the message wasn't being a little overeager, that's always available, so you can go back and review all of the message suppression items. Okay, so we've already seen preconditions here. We looked at the post conditions for that routine next word, just to verify that it could return a zero length string. But there are other kinds of as-built documentation. The as-built documentation shows up in gray. Doesn't have any line numbers because it doesn't really exist in the source code, but it's presented here as though it were comments, in this case written by your friendly CodePeer tool. So let's look at some other as-built documentation. So the first case we're going to look at is back in input, and it's the getChar routine. Actually, let's go back to the CodePeer report, and we'll look at input, and then we'll scroll down to the getChar routine. There we go. And in this routine, we have a new little grouping here of as-built documentation called test vectors. So the purpose of test vectors is to help someone who is trying to be certain that their test suite actually covers all of the paths of execution within a given function. So if someone's writing, let's say, some requirements-based tests and so on, and they want to look at the test to be sure that they really do handle all the different relevant inputs and so on, getChar CodePeer has noticed that there is some control flow here, if end line, then read new line. And it has identified the values of this expression that will determine whether or not you take one path or the other. That is, whether you execute read new line or you skip past it. And it's done this, it's helpfully looked at the end line procedure and determined what controls what it returns. And as we can see here, it is comparing last char and first char, and based on the value of n, which in this case is 1, it's determining whether to return true or false. And so what it's saying is that we want to be sure that we execute both paths through here. We need one of our tests to include a set of values such that last char minus first char is negative. In other words, last char is less than first char. And some other set of our tests must include the situation where last char minus first char is positive or 0. In other words, last char is greater than or equal to first char. So this is a pretty simple test vector. It's really just saying that we need to have at least 2 tests. We don't care about the actual value of this, except is it negative or is it 0 or positive? We might have more than just 2 subranges here for more complex control flows that might say, if it's in a certain range, then we need tests that have this value in 3 different ranges because there's more complex control flow controlled by this value. But in this case, there's just 2 possibilities. Either it's negative or it's 0 positive. And so long as your test suite includes both of those cases, you will in fact execute all the paths of this procedure. Now, this is a very simple procedure. As the procedures get more complex, you can imagine the set of test vectors also gets larger. It may depend on multiple inputs, different comparisons between inputs, and so on. But this can save you a lot of time when you're trying to quickly establish, well, what are the different kinds of control flow and what are the inputs that control that. The last item I want to refer to is also in this same file. There it is, read new line. Okay, so what's different about this one? Well, we see we've got some test vectors here. We've already learned a little bit about that. We've got preconditions, postconditions. There's this one in the middle here that is new. It's a presumption. A presumption is generated when there is a call on a routine that CodePeer did not analyze. So ada.textio.getLine is being called right here. And in this run, we are not analyzing all of the runtime system because that's a large piece of code. It's not really where you're interested in. You're interested in the bugs and so on of that. On the other hand, when you make a call on a procedure that CodePeer has analyzed, it knows the pre and post conditions for that procedure. When you call a routine that it has not analyzed, it doesn't have any information about those procedures. So it can only glean the characteristics of this routine by what you do with its output. And so what it is telling you here is it appears to be you are assuming that the result returned by a call on getLine in the out parameter last, that's this second parameter, which was called on line 227, that @ sign 227 means we're talking about line 227. This call, the out parameter last, is less than or equal to 1023. Now, CodePeer figured this out by looking ahead effectively. So, well, what did you do with with last care? Did you use it in a way that would make CodePeer be able to determine that this is an assumption you're making? Well, right here you use it. You also use it down here. And this is the one that's a little bit scarier. Here we simply use it to put out the line for echoing purposes. But over here we use the value returned in last care to add at the end of the line a carriage return. So we're adding 1 to last care, and we're using that as an index into line. Okay, so that's interesting. What that means is we are assuming that there's at least one empty, unused character at the end of line that we can then overwrite with a carriage return. There's a problem, though, and that is that getLine can, in fact, return 1024 in last care. If you look at the logic of getLine, it could return any value in the range that correspond to legal indices into this array, line. And line, if we look up, has indices 1 to 1024 defined. So there is the possibility that getLine could return a line that is 1024 lines long, and last care would be 1024 in that case. And this would be fine, but then in this case we would get an index out of bounds. So CodePeer, by looking ahead, it said, oh, you're making an assumption that this out parameter is less than 1023. And that turns out to be normally a very safe assumption, but it's exactly the kind of thing that a hacker would love to notice and put in a line of exactly length 1024 and then cause this thing to crash. Or if it were C and there were no runtime checking, it would simply overwrite some perhaps important piece of data with a ASCII carriage return. So this is exactly the kind of thing you don't want to leave in the code. So one fix for this is, instead of passing in the whole line, we could have passed in a slice that went from 1 to line tick last -1, leaving one extra character there so that we could then fill that in with an ASCII carriage return. And there are other ways we could solve this problem. We could just check to see if the line is too long and complain. There are various other ways. But right here, we're leaving ourselves open for a crash if the user types in a character of, a line of length 1024. So that's what CodePeer is good for. It looks at every one of those, possibilities that you would never worry about. It worries about them, and that can be very useful. So, okay, so I think we've pretty well covered the features of CodePeer, at least for sequential programs. There is a report that we will save for let's say, the next more advanced webinar, where it will analyze a program that has multiple tasks, looking for potential data race conditions, where you have two tasks that are referencing the same variable without proper synchronization. So it's a piece of data that's not inside a protected object, let's say, and you've gone ahead and referenced it from two different tasks. CodePeer is quite good at figuring that out. This particular simple problem doesn't have that, and that's sort of another dimension on CodePeer, which we'll talk about at some other point. Okay, so I think we've covered that. Let's go back and kind of finish up our presentation. And here we are picking up our PowerPoint again, and we see that I'm going to reiterate some of the features of CodePeer here on PowerPoint. Scalable, it uses a bottom-up approach. We talked a little bit about that, but one of the important features of CodePeer is, instead of sort of starting at the top of a program and working its way down and requiring you to have a real kind of test harness that will exercise your program and provide all the interesting values, CodePeer works bottom up. And it looks at all the possible values that a procedure might receive and whether those might cause trouble. And it creates preconditions on the way up, and those are then checked at every possible call. We have an historical database that keeps track of every time CodePeer is run, and it allows you to focus just on the new problems or look at the old problems. You can, for example, if you ran CodePeer once on a good baseline and then you ran it again on a updated baseline, you could choose to only look at the messages that had been added and ignore the original ones that are the same as before, if you presume that those are all those are all fine. You're presuming those are all okay for now, and you can just by clicking on that added versus unchanged, you can decide which ones you want to look at. It's integrated with the front end. That's not only in general, but it's also now it's built into the installation system, so you don't have to worry about installing cont'd as a separate tool. It's built in. Other important features, CodePeer is designed to be sound in that it uses conservative assumptions. It doesn't particularly want to say, oh, that's fine, when in fact there's a chance it's not fine. Because of that, it shouldn't have any false negatives. That is, it shouldn't ever say everything's good when in fact everything is not good, at least for the things that it checks. Now, CodePeer doesn't check to see that you used exactly the right algorithm, but it makes certain that the algorithm you did use will not cause things like array out of bounds and uninitialized data to be used and so on. So it can't find all your bugs. That would be nice if it could, but it can find places where you might run into a runtime failure, or you did something suspicious, like you didn't use the result of some computation. On the other hand, it can be over picky, and you end up with some false positives. It's sort of the halting rule says that we can't actually precisely decide whether every program is correct or incorrect. So we err on the side of false positives. We try to give you a ranking which will reduce the number of cases of high or medium ranking false positives, but there are always some tricky algorithms that we have to sort of assume the worst. But we try never to give you, miss something. It's very precise, and it's always getting more precise. It uses a number of techniques that are give it very precise representation of the possible values. For example, with that um, suspicious precondition, we knew that the incoming value for last had to be in the range 2 to 199 or 201. So we're able to represent not just contiguous ranges, but discontiguous ranges. So we have very precise set manipulations going on. And as mentioned, it's a bottom-up structure so that we don't run into some of the scalability problems associated with kind of a top-down approach. Flexible, incremental, and so on. This is sort of motherhood. It's good, good, good all the way. We have made a strong effort to give this very modern and flexible features, and we've continued to enhance the product over its ongoing lifetime, and we'll continue to enhance it in the future. So as an example of some of these enhancements, CodePeer 2.3, we have full support for Ada 2012, as well as Ada 2005, Ada 95, and Ada 83. So it really covers all the bases as far as the different generations of Ada. Ada 2012 being particularly interesting because it now allows users to specify pre and post conditions, in addition to CodePeer inferring them. And in fact, you could look at the ones that CodePeer inferred and then add those explicitly if you find them to be useful. And now they would be checked at runtime by the compiled code, as well as being checked statically by the CodePeer tool. We've enhanced the analysis of floating point values. We used to simply do infinitely precise calculations, which didn't match what the hardware was doing. Now we can simulate calculations using IEEE float precision, so we know about possibilities for underflow, for example, which we now, in the past, we just ignored underflow, and we can also identify overflow possibilities. Also, we're doing more advanced analysis of global variables and whether they're initialized somewhere in the program by the elaboration of library units, and so that gives you more precise information about whether global variables are properly initialized before they're referenced. Race conditions, we didn't show that, we talked about it, but there are additional reports now to give more information about race conditions. Fewer false positives in a couple of ways. We have the notion of conditional preconditions, which are preconditions that only apply if other inputs have certain values. So we might say, well, x must be greater than 0 if y is also greater than 0, for example. Those kind of conditional preconditions allow us to, again, be more precise. Unused assignments, we've done more work in terms of analyzing those and describing them more precisely. We are incorporating more information from the Common Weakness Enumeration, CWE, which is something that a number of departments in the Department of Defense are interested in these days. They're related to the possibility or the number of vulnerabilities and weaknesses in your code as far as hacking and so on. And we now include CWE IDs in our export for spreadsheet representation, and we're on our roadmap, we are adding CWE message IDs in other parts of the output. As mentioned before, it does include the GNAT front end. You don't have to separately install it. Okay, so that's the full story on CodePeer 2.3, and we certainly welcome your interest in the product and to contact our sales organization if you would like to receive an evaluation. Thank you very much.